Hey, welcome back to Math with Patrick. It's May 9th, and we are solving problem number 129 from the Daily Epsilon calendar. And the answer is 9, that's today's date. We need to find the number of line segments in the complex plane that connect two of the sixth roots of 1, where at least one root is real. Okay, a lot of vocab. Hopefully line segments, not too tricky. That's just kind of some straight line that has end caps. Complex plane. This is kind of like your standard like XY plane, except instead of X and Y, we're gonna represent different kinds of numbers on the plane where there is a real part. And this is just like any normal number line between like negative infinity and infinity, and some kind of imaginary part. And I don't know, for me it's kind of hard to explain like what the imaginary part is. Like maybe you've worked with like quadratic equations, and you know that the negative or the square root of -1 is this number I. Essentially complex numbers will have some kind of real part like the number 2, and then some kind of imaginary part like maybe, I don't know, some real number times that I. And the positive imaginary direction is up. So I would graph this complex number maybe right around like here, because I went 2 in the real direction and then 2.5 in the imaginary direction. Okay, so we have our complex plane. We need to make line segments in the complex plane, kind of like this. And these line segments need to connect the sixth roots of 1. A sixth root of some number is some number that we don't know just yet, where we multiply it over and over and over and over and over again 6 times, and then we get 1. So this is what a sixth root kind of looks like. Essentially, it's just this number, and I'm not really sure what it is right now, where if I multiply it 6 times over, I get the number 1. And then finally, I'm going to find those sixth roots in the complex plane and then connect them with line segments. And one of these dots on the complex plane has to be a real root. And again, real just means somewhere along my real axis. It does not have an imaginary part, so it's not kind of floating off to the top or the bottom. 2 of the sixth roots of 1 should be fairly easy to verify. It's basically just going to be 1 and -1. Because if you put the number 1 here, 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 and here, and multiply it all together, you're going to get 1. Also, if you stick a -1 in all of these spots and multiply them all together, you're going to get 1. So I found 2 of the sixth roots of 1, but with complex numbers, there are more. Essentially, we're doing this like polynomial, I guess, polynomial equation. We're trying to find x to the sixth, and when that's equal to 1, maybe I could subtract the 1 to this side and get something in some kind of like standard form. And anytime you're working with polynomials, you're going to find the same amount of solutions as your highest power, or this degree. So the 6 right here is the degree of the polynomial. It's also the amount of complex roots I'm expecting to find as an answer. As in, there's going to be 4 more kind of somewhere around the complex plane that also, when I raise it to the power of 6, I get 1. And I think I know exactly where they are. There is a way of thinking about powers of complex numbers in terms of rotations. And I don't know, if you haven't seen this before, bear with me. Let's start with this -1. When I raise -1 to the power of 6 in the complex plane, I'm thinking about it as 6 rotations, where you start on the real axis, and the first power will bring you to your number. The second power of it will bring you exactly that same amount of like angle. Essentially, this was like 180 degrees. And so squaring some kind of complex number in the complex plane looks like a rotation. And so the next one will be the exact same degree measurement, 180 degrees. And I'm going to keep going around in this circle. And once we do -1 squared, I get back to this 1. And we have this like interesting pattern where if you do the next power of -1, you're going to rotate over here again. And then -1 to the power of 4 brings you right back to this number 1. And instead of thinking with like weird square roots and like these honestly kind of difficult complex numbers, I'm just going to think about it in terms of rotations. I want to try to find some kind of spot somewhere in this circle where when I rotate it by some fixed angle 6 times, I'll get back to the number 1. So the next easiest one for me to find would just be whatever 360 degrees divided by 6 is. Because when I do that angle and I kind of go around the circle 6 times, I will get back to the number 1. So this is exactly 60 degrees. That's going to be right around here. And if you imagine thinking about powers of complex numbers as rotations, then you can see that the first power will bring me here. The second one will be here. Third, fourth, fifth, and then finally the sixth will bring me back to the number 1. And I kind of actually just traced out all the other solutions. There's going to be another one here. You can imagine the rotation being 120 degrees this time, and that would be to the power of 1, to the power of 2, 3, 4, 5, 6. And then since I do 6 multiplications and I get back to the number 1, that is a 6th root. And then the other 2 are going to be hiding right here and right here. So this kind of looks like a unit circle to me. I mean, it basically is, right? There's a radius of 1, and I just have some points along the circle. And I'm just using what I know about special right triangles, specifically this 30, 60, 90 triangle, to get the coordinates of my other points. I guess I don't really need them, honestly, because I just should connect them with line segments. But I'd like to at least label what those points are, what the 6th roots of 1 are. This first one is just 1, 0. This one is -1, 0. Or I guess if I'm expressing it as complex numbers, they aren't points, but rather just numbers. And so this would be like 1 plus 0i, and this would be -1 plus 0i. This point right here is half in the real direction. And again, I'm getting these numbers because I know my 30, 60, 90 triangles. So I'm going to go half a unit in the real direction and √3 over 2i in the imaginary direction. Then for this point, it's -½ plus √3 over 2i. This one is negative in the real direction and the imaginary direction, so it's going to be negative on both of these values. And then finally, this point right here is going to have a real component of 1/2 and an imaginary component of -√3 over 2i. Cool. So those are all of my 6th roots of 1, or the 6th roots of unity, as they're sometimes called. Okay, I didn't really need to label all of them, but I wanted to. Now let's connect these with some line segments. And it's now a counting problem, essentially. We just need to count line segments that connect these. At least one root is real, so all of my line segments need to start or end at either that point or the other point. And I think let's just try it out. It doesn't seem too hard to just count straight up. So here's going to be 1, 2, 3, 4, and 5. And then let's color code the other one. I want to start at my positive real root, and I'm going to basically draw the same picture. 6, 7. I won't double count the middle one. It's already there. 8, and then 9. So those are all of my line segments connecting the 6th roots of unity in a complex plane. And yeah, there's 9 of them. So we just kind of made a fun little connecty graph with dots and or vertices and edges, basically. And that's the picture. There's 9 of those line segments that connect the 6th roots of unity. So we're all done. Hope you enjoyed. I'll see you tomorrow.